In section 13.4 of chapter 13, the topic is testing the significance of the slope. In the previous section, we obtained the regression equation by running the regression command. And at the end, I told you about the coefficients here that shows 1998 for the intercept and 0.26 for sales calls. In other words, the regression equation is the estimated value of y hat equals 1998 plus 0.26x. So if you substitute any value of x here in this equation, you predict the value of y. So let me put that formula here in the simple version: equal 1998 plus 0.26 times x. But x can be any value, but I'm just going to select the previous, all the known x values that we have from the sample, which are, in this case, the first one is B4, the 96 calls. So if I hit enter, I get a predicted value for copies, predicted value. And so for 41, instead of 41, I predict 4494. And copy this, and I get all the predicted values for every other. For example, in this case here, for 36 calls, the predicted value is 2934. The actual value is 28. All right. Well, my model for the prediction of copiers sold, it is relevant as long as the slope of the line is relevant. And in this case, this value 0.26. Is it relevant? So in the computer, the computer runs automatically the following hypothesis testing. The null hypothesis is that the beta is equal to 0. It is not written as B because this is the B version of the population, which is called beta. And H1 is beta is different than 0. And so remember, you obtain a regression equation like this: A plus bx, where this B is the estimated value of beta, the population parameter, using the sample. And the computer will do this, which is, if you notice, a two-tailed test for beta using B. Well, how is that done? Well, if you recall from a previous chapter, the z-value in the sampling distribution of x bar, chapter, the z-value is calculated as x bar minus mu over sigma over the square root of n. And if we did not know sigma, then the formula is x bar minus mu divided by s over the square root of n. And this value of mu is the value of mu with the equal sign in the null hypothesis. Well, the computer does this. It takes the actual value of B, of beta, I'm sorry, B is as estimate of beta. Okay, so we substitute the x bar with a B. We subtract the actual value, the value suggested in the null hypothesis of B for the population parameter. In the previous case, for the mean was mu, but now it is beta. In the null hypothesis, beta is equal to 0, so we write 0 here, divided by, if you recall also from the previous chapter, this thing here is called standard error of the mean. So let's just call that standard error. And in this case, it'll be the standard error of B, the slope. Well, let me go back here to my, let's see if I don't leave this, if I keep it. Here in the results, I get my coefficient for the sales cost for X is 0.26, and I get my standard error. So 0.26, as suggested previously, 0.26 minus 0 is 0.26. Divided by the standard error, I get the test statistics. Okay, so 0.26 divided by 0.042, I get the test statistic that is 6.2. This is what I'm going to use against the critical value for testing the null hypothesis. Well, what is, in case suppose that you require that, what is in this case, let me write it right here, right below, T critical value. Remember, we don't know sigma, so we have to use the T distribution. Well, this is equal to T IMV. Remember, inverse is to calculate a T value. And notice that it says, if I just leave it like this, it says returns the left tail inverse. So I have to put my left tail. If it is a two-tail test at 5%, my upper tail will be 0.025. So the remaining tail to the left is 0.975. So let me just put 0.975. And then comma, the degrees of freedom will be, in this case, 13. 15 minus 2, n minus 2. And my critical value will be 2.16 for a two-tail test. Suppose you're doing a one-tail test, and then it'll be equal T dot inverse again, and instead of 0.975 here, it'll be 0.95 because 0.05 will be on the right tail. And again, the same degrees of freedom. The value will be 1.77. So I think in your book it shows, what if you're testing whether the beta, the population parameter of the slope, is greater than 0. In other words, you're just testing whether it is positive. So in that case, it'll be a one-tail test, and all that changes is the critical value. So, okay, so this will be for the two-tail, this will be for a one-tail. And Excel automatically does a two-tail test. So following the two-tail test, the test statistic 6.2 is obviously much larger than the critical value of 2.16. So therefore, reject the null hypothesis and argue that beta is significantly different than 0. And notice the p-value is 3.19 with 50 to the left. So that value is actually 0.1234319. Okay, so that is the p-value. Well, that value is definitely less than 5%, so reject the null hypothesis. And the slope is significantly different than 0. Now, what if you were testing that is greater than 0, one-tail test? Well, notice the critical value will be 1.77, and 6.21 definitely is larger than 177, so you will reject the null hypothesis too.